Okay, so now that we've seen the definition of how impedance is going to work, we're going to do a quick example to just get practice with it. I do want to point out that on this circuit, I've already converted all the resistors, capacitors, inductors into impedances for you, and that will be true for some of our examples, but really what you should get used to and what you should expect for the exam is that you're going to have to convert those into impedances yourself. So I'm not usually going to give it to you here. But regardless, we see things in terms of J. And so even though this is an inductor and a capacitor, I can combine them together. So I have 4J in parallel with a negative 2J. And you know the rule for that is going to be 4J times negative 2J over 4J plus negative 2J. That's going to be, see, 4 times negative 2 is negative 8. J times J is J squared, which is negative 1. So that works out to be a positive 8 on top. And 4J minus 2J is 2J. So that's 4 over J. And you can actually convert that then. So dividing by J is the same as multiplying by negative J mathematically. So we get negative 4J there. So that means this whole thing here is the same as negative 4J. And then I'm going to go ahead and combine these three things in series, as well as these three things in series. And I will also combine those two in parallel. So let's see, I have a 1 in parallel with a negative 2J. That's 1 times negative 2J over 1 plus minus 2J. It's going to work out to be a negative 2J over 1 minus 2J. Now I'm not going to try to simplify that just yet. We'll leave it for now. And let's see what we get here. So we have from node A coming in. Now since a combination of a resistor, inductor, capacitor is neither one of those three things, we're just going to use boxes here. So this box is going to represent the combination there, which we said is negative 2J over 1 minus 2J. Then we're going to have the green one here. And those three were in series, so you can just add them up. 2 plus 6J plus a negative 2J is going to be a 6 plus 4J. Then we have this red one here. And so we see that it was 4 2J and minus 4J in series, so you add that up. That'll be a 4 minus 2J. Combine these together. Then we see we have the green and red in parallel. So that's going to be 6 plus 4J in parallel with a 4 minus 2J. So that's going to be 6 plus 4J times 4 minus 2J over 6 plus 4J plus 4 minus 2J. And let's see here. The bottom, that's going to be 10 plus 2J. The top, try to do a little bit of work here. 24, and then it's going to be plus 8 is going to be 32. And minus 12 plus 16 is plus 4J. And, I mean, it's kind of a mess here. But let's say divide top and bottom by 2, I'd have 16 plus 2J over 5 plus J. And then finally, this result here is in series with the purple. So your overall answer then, Z equivalent, is negative 2J over 1 minus 2J plus 16 plus 2J over 5 plus J. And then we want to work around and see what that's going to be. Now it turns out your calculator can do imaginary number arithmetic. And so I'm going to put this in my calculator here and see what I get. Save myself some time of trying to do all that algebra there. And what I get, if I round it, is 3.95 minus 0.63J. So that right there is the equivalent impedance. And if you want, you can go ahead and convert that into a polar version of it. And by the way, your calculator can also do polar. It's going to be 4 angle negative 9.1 degrees. And for a problem like this, I don't care if you write it in rectangular or in polar coordinates for the equivalent impedance. Either way is fine. But this is how we handle this.